Okay, so I'm gonna review the materials covered for exam one. I'm gonna record this. Session. Now, standard disclaimer, these are the things I consider to be important, not necessarily have everything that you find important. Okay, so if it's not on here, that doesn't mean it won't be that you will be responsible for, right? It's still the stuff that maybe I take for granted, but better for you to have on your notebook. Okay, so just take this as a more of like a, there've been a lot of equations, a lot of things going on. This is more or less a chance to sit down and see kind of how everything is put down and how they're used. And then feel free to ask any questions at any time. Specifically if it relates to any, like what we're doing relates to any problems we've done. That's the great chance, a good chance to talk about things. So in this exam, the first thing you'll be tested on are vectors, okay? And if you've never seen vectors before, it's understandable that they seem to be very bizarre and complicated objects. But really, a vector is an arrow, right? That gives you both magnitude and directions. It tells you the length of the arrow tells you how much something is, and then which way it's pointing tells you the direction. But it's always with reference to an angle. So if it was the x-axis, it'll be a certain angle. In math, counterclockwise is positive, and then down is negative. Clockwise is negative, but it doesn't have to be with reference to the x-axis. You've seen problems where it's reference to this axis, right? Or reference to this one, so it doesn't matter. You don't have to stick to any one. So this is a vector A, and we could also put this vector in a Cartesian coordinate system where it could be direct x-axis, but the direction is given by I. Okay, it's just the way people started out. Instead of calling it x hat, they call it I hat. Sorry, this is wrong direction. So that's j hat. X is actually over here, I hat, and then z is the k. Okay, and so once you put into these coordinate system, it kind of lets you figure out how to get to this point. This point up here is ax, ay, az. Okay, and how do you get there? Well, you walk over ax amount, and then you walk over an amount ay, and then you go up an amount az. Okay. Ax, ay, az, these are called components. And we can write it in component form. And just the sum of ax in the I component, ay in the j component, j hat, and az is the k hat, or k component, like that. Very important that if this is height as a vector, then you either have to have another arrow on this side or hats. So that's what's called component form. the length of the vector is written without the A, or you write it without the vector symbol, or you write with the vector symbol, but this symbol, which used to have absolute value, now means more. It means the length. So we use the Pythagorean theorem to get the full length, right? And then there's something called unit vector. The unit vector has length or magnitude 1. So if we treat these I hats, J hats, K hats, they're distinguished by these hats. They all have 1. So you can write that. So why is it important? Because it it only tells you the direction. You always know that the length is 1. So a regular vector can be written as its length times its direction. So you kind of separate it out. Here's the length. Here's the direction, right? So if you solve this for a hat, someone asks you, hey, what's the unit vector for this? You just take a and divide it by its length. The other way to represent a vector is just graphical form. So you have a, and say it's theta. Now, in components again, this will be so x a1 and a. If this is the angle theta, then ax is the hypotenuse times cosine because it's adjacent to it. And this is the sine because it's opposite. Okay, so you can, someone switches on you and says, hey, what's the angle between them? Well, then you can see here, you can quickly solve for the angle by dividing ax by a, for example. And then you can add vectors. If you have a vector A and a vector B, you add them by move. Graphically, to see what it is, you have to move it so that the tail of one is touching the head of the other. Doesn't matter which one. So I can either move B, or I can move A. Right, so the tail of A is now touching the head of B. And then I connect the tail of one to the head of the last one, and that's A plus B. If you're given Cartesian coordinates, then it's very easy. AX plus BX. AY BY plus AZ plus BZ times K. That's very important. I think the biggest mistake students do when they add these two vectors, they just forget about these i's, j's, and k's, and they just add them all up and get one number. Okay. These things are like placeholders. They keep things in order, right? Only the x components can add. Only the y components can. Only the z can. Any questions? Okay, so if you're like an example, here's the biggest example is when you have to do this, a projectile motion problem. Right? They're gonna give you an initial velocity and at an angle from the horizontal. And if that's all, immediately you should be able to write down the components. Okay? Immediately, you should be able to write V0 cosine theta, V0 sine theta. Immediately, you should also be able to write V0 like squared, that's V0 y squared. And it's the velocity vector that determines an angle, the launch angle, okay? It's not the distance, okay? It's not the distance. Remember the thing with the shooting the monkey or the archer fish? That angle is different from the angle that you launch, okay? The angle that you launch is determined by V naught, nothing else. And then don't forget units. The last thing we can do with vectors is multiply a simple form of multiplication called scalar multiplication, and all you're doing there is increasing its length or increasing or decreasing its length. So remember, scalar is just a number. Vector is what we've been talking about. So vector B, you take a number, a scalar A, you multiply by the little a, you get a new vector that if A is 1, then nothing's changed, but if you can stretch the vector or decrease it, but in the end, both these vectors are in the same direction. The only thing different is one's longer or shorter than the other, okay? Okay, So now we got that out of the way, we can talk about motion. That's what we started the course with. Yeah,
What's little a supposed to represent?
the what?
What's the little a supposed to represent?
It's just the scale,
Oh,
okay, or this number. Just a number. Yeah, it has no I had. Okay, first thing about motion is we have definitions. So you should remember all your definitions. Okay, so for example, position. And now that we know how to write vectors, we'll do the general case where a position is actually a vector. Right? Remember, it's that point X, Y, Z. So X would be the X component, and Y would be the Y would be the Y component, and then Z would be the K component. So that's the vector, the position written as a vector. When we began, we just did one dimensional, but now we do all three. Two would be the displacement. And that's just the change in position. Okay. Our final minus our initial. It's always final minus initial, this symbol delta. So it's just a change in X, I hat, change in Y, J hat, change in Z. Yeah. And then we did things to the displacement. First thing is velocity. Or that's instantaneous velocity. Oh, by the way, let me actually, to go with displacement, there's something called distance. And distance now, if it was one dimensional motion, it was just absolute value sign, but now it's the length of the displacement vector. So it's just delta x squared, delta y squared, delta z squared. And you can see that it can never be negative because you're taking the square sum of positive numbers. Third is velocity. And this is a instantaneous velocity. All right, and you had some problems. It's defined as the time rate of change of the position. A lot of you in your homework are a little confused what to do. Do I put the time in and then take the derivative, or do I take the derivative and then put in the time? You always take the derivative first. Okay, and then put in the time, because if you put in the time in, there'd be no more t would be gone and you couldn't take the derivative. Okay, so you always have to take the derivative first and then put in the time to see what that velocity is at that time, right? Average velocity.
Question 3 was instant velocity.
Huh?
Question 3 or 3 was instant velocity.
Yeah, this is instantaneous velocity. So from now on, we introduce that instantaneous, but whenever we hear velocity, it means instantaneous. Because when we really want the average, we have to say the word average. Average velocity. Okay, and that's gonna be delta V delta R over delta T. Okay. So which one is the slope of the curve? Well, it's gonna be this one. Okay, the slope of a curve is the derivative at that point. And you saw that if you we look at R as a function of time, the slope will be dr, at this point will be dr dt. But the average is something between two different time zones. This will be delta t. This will be delta r. I'm doing the really one-dimensional here because we can't show it three-dimensional. So the instantaneous derivative, the velocity, is the slope of this position. Five would be acceleration or instantaneous acceleration. And the idea is the same. You're taking the derivative of the velocity with respect to time. Which, if you took the derivative again, if the velocity is the derivative with respect to time, then we're taking it twice. That's the second derivative of position. And then average acceleration. Same. Oh, wait. I didn't mean to write delta here. I mean to have push average. E average. So A average is delta V. Is everybody clear about this? When will you use this? Well, this is for number one, it's like a concept, okay, understanding it. That things are the slope of the other things, like acceleration is the slope of the velocity curve, and the velocity is the slope of the position curve. When will you use it? Well, if you're given something explicitly as a function of time, then you can use it. That's when you take the derivative and find everything, right? Like in homework 1. But if they don't give it to you, then it might be useless, right? We can't do anything, right? They might, if they don't give you the function, you can't take the derivative. But if they give you a curve, maybe graphically, then you can kind of say, hey, well, I know at this point the slope is flat. That must mean the velocity is 0, right? So that you can use it. They don't have to give you a function, but they can give you graphs in which you can answer qualitatively what's going on. Oh, remember, find the steepest part. Okay, so we're done with the definitions. We now go a little deeper when the motion, the acceleration is constant. So B would be when things have a kind of constant acceleration. Okay, so only when you know it's constant, and sometimes we can say, hey, this part is constant, but then it changes. So we can treat this one segment to be constant. And then we derive the three equations of constant acceleration. And I'll just kind of put it in vector form so that it's very general, but it's up to you how you want to use it. So if I say V0 equals V naught plus A as vectors, I really mean three equations, right? You have Vx equals V naught x plus AXT, Gy equals V naught y plus AYT, and then DZ equals V naught C plus AZT, where A equals AX squared plus AY squared plus AZ squared. And all these A's are constant. And then the second one would be R equals R naught plus V naught T plus 1/2 AT squared. And then the third is V. Now V squared is no longer a vector, right? V naught squared plus 2 A x plus delta x plus A y delta y plus A g delta z. But if you just want one component, then just throw the other ones out and just put x's. Yeah. Say if you want the x equation. Okay. And now we go to the next type of motion. Which we're gonna call projectile motion. And we're gonna lump it with free fall as well. Because really, free fall motion, when something's just falling, it's really projectile motion where there's no velocity in the x direction. So if you can see that projectile and free fall being the same, then it makes things easier to look at everything. First of all, we take the y-axis as positive and up, right? So going up is going to be, that direction can be y and going to be a positive. We those equations we wrote down, that means ay is minus g. Okay, and g is always a positive number. Okay, always 9.8 meters per second squared. That's why we put the minus sign to show that it's going down. And then AX and AZ, those are horizontal to Y. And there's no acceleration, okay? So in projectile motion or free fall, there's only acceleration in the vertical direction, none in the horizontal. Okay, and usually we let V0 the horizontal, if there's horizontal motion, we call it V0x. Okay, so I like to then take those equations and turn them into a new set that we can use. So y equals y0 plus v0 t minus 1/2 2t squared. And then the third is v equals x equals v y squared equals v not y squared minus 2g y minus y naught. And then fourth, I hope you can still see this. Is x equals x naught plus v0x. So standard procedure, you it can be launched from a flat ground or from a cliff. There would be a initial velocity. They would probably give you an angle, right? And the curve will trace out a parabola. You choose your origin. You can either choose it up here or down here. Usually, we do it at where we start. So that would be 0, 0. That means anything that's below is going to be negative. You're having a hard time.
Just over the top of the computer.
Okay, x equals x naught plus v naught xt.
Yeah.
Okay, and again, we write out v naught x. Every year, I mean, this year, like probably, I've said this 3 times already, but people, for some reason, don't see this. V naught y, v naught sine and beta. Okay, those are the components of the initial velocity. And they can be written like this.
So I said,
V naught y.
okay.
This is just V naught. Okay, so you shoot it. Only if it's level ground are things symmetric, right? So if it was a level ground, then the initial velocity and the final will be the same. But if it's not, then you can't say that. Only if it's level ground is the angle that it hits the same, okay? But if it's not, you can't say that either. So this is not level ground. This will be some different angle. So this right here will be the final velocity, right? Vy. And this will be some other angle that's not the same. This distance, say this distance is h, that's a distance. But the actual displacement though would be, if this is x, then the actual displacement is x minus h, right? And then where do you achieve the highest point? What's special about that?
There's
That's
no,
Huh?
there's no horizontal velocity,
I think you wanted to say the other thing. There's only horizontal.
only horizontal.
Only, yeah. So there's only V naught X. V naught Y is 0. And that's the same as this one. Because there's no acceleration, it stays the same. Again, V naught, I'm writing it again because people don't see that they're all connected. V naught is equal to the components squared, you add them up, and take the square root. Any questions? No. X and Y motion are independent. Now, probably one thing I want to say is, remember we said before, you try to pick your equation. If they don't give you t, for example, then you go to the equation without it, right? And then the idea is to find an equation that has the things you have, but not the thing and the thing you don't have, but it's also the thing you want. So one unknown and the others are known. However, if you have more than more than one thing going on, then it's okay. You might have two unknowns, but if you have two equations from each object, then you can still solve it. Okay. So if it's only one object, then you better find the equation that has only one unknown. But if it's two, you can find an equation with two unknowns, but at least as long as you have an equation for each. Okay. Next, the fourth type of motion, or third type of motion. Uniform circular motion. And something going in a circle, radius r. Uniform just means that the speed, that this v vector, the speed is constant, it doesn't change. The vector itself is changing because it's pointing at different places. What's going on is that there is an acceleration, and it's called centripetal acceleration, right? And it's responsible for changing the direction of this vector, but not its magnitude. In order to change something's magnitude, it has to have a component that's parallel, but a centripetal is always perpendicular. So all it does is change its direction. You derive v squared over r. So I'll get centripetal acceleration. And it always points to this letter. And always perpendicular to the What happens if you got rid of it while it's moving? If it's suddenly, if you have it, it's on a string and you're going in a circle, if you cut the string, the velocity now has no acceleration, it'll always go where it was last, right? So if it was pointing down, it'll continue to point down. If it's pointing this way, it'll continue to go that way. So it'll go, takes out a path that's tangent to the circle. Right? That's what happens. It'll go straight. The motion will be straight. So B always tangent. So if you're gonna do a problem, what you wanna do is choose a place, and they might not give you a picture. So you have to actually draw a circle, put the object anywhere you want, but once you put it there, then you have to draw everything that corresponds to that place. So if you're drawing it here, then AC will going to the left and it'll be negative. But if you put it over here, then AC is positive because it's going, pointing to the right. Okay. The other things that we use to describe this is T, which is the period. For revolution, right, of revolution. How long it takes to go around in a circle. The other thing is the, what's called the frequency, which is 1/period, and that's in revolutions per second. Okay, so if they give something revolutions per minute, or you have to change it to second. If they say it goes around 3 times a second, that's 3 revolutions per second. If they said the period was 2 seconds, then you can quickly find the frequency by just taking the. Then we have just a couple more equations. Like this. There's something called angular frequency, which is omega. And that tells you how much angle is changing. So if it goes around in 1 revolution, that's 2 pi radians. It has to be in radians. So it's 2 pi. And then you multiply by the regular frequency. So that if it's 1 revolution, that's 2 pi per second, right? Well, it's the radians per second. And this is called the angular frequency. And then the last 2 equations, so once we define that, then B equals omega R. And this is an important one, right? This is an important one. It tells you how fast it's going the further you are from the center. So the further you are, the faster you go. And you can do all the manipulations and stuff, and also show that the centripetal acceleration is omega times B. Okay, any questions? Okay, so the last type of motion is relative motion. The last type of motion that we covered in so far. And to me, I think the best way to remember or to deal with relative motion is with the picture. So, let's remember the equation. So if you have a velocity, it's gonna be written like this, where this means velocity of A relative to B, right? The velocity of A relative to B. Okay, so if you encounter a relative motion problem, your first task is to write down your givens, and you have to correctly name it. So we're talking about a plane is flying 500 miles per hour. That's relative, you have to figure out. Relative to the wind or to the ground. And then you decide it's to the ground. So then it'd be plane P, G, P relative to ground. Okay. There's velocity of B, C, that means velocity B of A relative to C, right? And then lastly, the velocity of A to BC. Or to BC, A to B.
AC is the last one.
AC, yeah. Velocity of A. Relative to BC, okay. Now you take any random two things. Take A relative to B. How do I remember the equation? Well, it's easy. A goes to the front of the first vector, meaning plus the velocity of the second vector, and C goes to the back, right? And what's in between is whatever you can put whatever you want, as long as it's the same thing. So B, B. You can put anything you want, as long as it's in the middle, after A in this one and before C on that one. So at the end of the day, you read the problem, and the last question is, what is the velocity of the boat relative to the water? That's what you're gonna put first, the velocity of B relative to water. Right, and then break it up into two things. Okay, and then figure out each one separately. Once you figure out each one in component form, it's just a vector addition problem. You're gonna add them together, component by component. Yeah,
Is this supposed to be AC equals AB plus BC?
that's right. I think that's right. This is right, right?
Yeah, that's right.
Yes, right.
Mhm. So that's what the way I wanted to remember.
Things cancel.
Oh, yeah, you're, this is C. I found this, yeah, C, right there. So, yeah, I'm separating this out, so it's A and C and then putting B in between. Thank you. And then the last thing would be knowing that VAB equals minus VCA. So if we switch a motion, it's gonna be opposite. So when you're moving relative to something, the other thing will see you going the opposite direction. Now, once, treat this like a vector addition problem. You gotta just figure out what the vectors are. Once you do that, break it into components and then add them together. Add or subtract. Okay, so now those are all the motion, types of motion. Now we can talk about forces. Okay. So forces. There's Newton's second law. That's the big thing. No, you're gonna get tested on. What is Newton's second law? How do you apply it? So forth. Newton's second law is a vector equation. Sum of all the forces. In other words, the net force equals the mass times the acceleration. It's a vector equation, which means that every component follows it. So MA times X, the forces in the Y equals MA times Y. And then some of the forces in the Z equals MA times C. So you have to satisfy the equation in all three components. And if you have more than one object, then each object must satisfy. Most of the time, though, there's no third component. And you might at most have four equations to deal with because there's only two objects. So you have to, whatever you put in one, you can't reuse the variable for the other. Whatever you use for one object, you can't reuse it for the other unless it is there truly. But you have to, because what you're gonna do is try to solve all the equations simultaneously. And if you're reusing variables that's not supposed to be reused, then you're gonna get the wrong answer. The other thing, advice I always give is, this is telling you what to do. So it's really just, you can think of it as instructions. You go through your free body diagram and find all the x components, right? You ask, does this, say you have a free body diagram like this, that way. So this is F1, F2, Fx. You go through each one. Does this have an x component? Does this have an x component?
Nope.
No, so you don't include it. Does this?
Yes.
Yes. And at this point, maybe you don't know what the angle is. It's hard to know. It's about a ramp that you haven't figured out. Don't let that mess you up, right? Just call it F2x. You can, at least you can see that this will be the component, F2x, right? And it's positive. We put positive. And then F3, does it have an x component? Yes. All on the x, and it's negative, so minus F3. Right? The biggest mistake too, and then students continue making this mistake all the way to the final. Is they see this M and they just write M. This M has to be the mass of this object, okay? So if this was big M, you have to write big M. Okay, that's the most common mistake. And the second most common mistake is put in the acceleration. Most of you didn't do it in the homework I just graded. But if you do, it's great. If you put in the acceleration, which way it's going, let's say it's going that way. Okay. Then everything that you need to know is in this diagram. Including which direction the acceleration is in. In this case, does it have an X component? Yes, it has only the X component, no Y component. And it's in the negative, so you have to put this minus sign. And then the next line is when you kind of figure out what 2x is. So this was the theta, and the next line would be F2 cosine theta minus F3 equals minus M. And then you do that for the Y. The Y, F1, are you, do you have a Y component? Yes. Negative, and it's positive and negative. Does F3 have a Y component? No. Does F2? Yes. The positive and negative, well, it's going up. Plus F2Y equals big M, don't put little m. You put whatever the mass is supposed to be, M1, M total, whatever. And then times the acceleration, which is 0, as it's not moving, okay? So this is what it means to draw a free body diagram and apply it to apply Newton's second law. Free body diagram, here's Newton's second law. This is applying, okay?
Will we ever get like I know it's unlikely, will we ever get like a free body diagram where you have to consider the z-axis as well? Or is it just X and Y?
Just X and Y, yeah, you know, it's it's just another thing, but not, you won't, not in this class.
Okay. But later or never, hopefully,
No, never. I could give you two, but
please do not.
it's just another set of equations.
Just one more thing, that's all.
Yeah, that's another thing. You'll be expanding your mind to the third dimension. So the exam, it's gonna say, draw a free body diagram. Please know how to draw a free body diagram. Okay? Apply Newton's second law. This is what it means. There's no anything else. After that, you can make a mistake, you can make an algebra mistake, you can do all this stuff, get the wrong answer, it doesn't matter. But this is what is the most important thing, this, and then knowing how to turn it into an equation, okay? So I have to tortuously, I have to go through and see that you get it, do the algebra right to give you some points, but this is where I'm looking at the bulk of what you're trying to do, okay, making sure it's right. If this is wrong, you're gonna get the wrong answer, right? Okay, so is that clear? Okay, so if you don't even draw a free body diagram, there's no way, right? Yeah.
Do you like put a capital M like no matter what? Or,
No,
like-
this was an example.
Oh, okay.
Okay.
Like how
So-
do you know that the M was capital? Like as stupid
How-
as that sounds. Yeah.
Well, it in the Times Roman numeral font, it's gonna be capital or small, so you have to pay attention to those things.
Oh, okay. Like will that it'll say it in the problem? Like,
I mean, it will show you that this has mass big M and this has mass small m.
Is that M just pointing to like the dot, like the point which is referring to like the object.
Yeah.
Okay. So we have to include that, like the mass in our free body diagrams.
What I told you in class, in the lecture was, you can put it over here.
Oh, okay.
This,
Right.
but I didn't have space, so
Thank you.
technically, when I learned it, this dot is labeled M, whatever mass it is. So it can be M1, M2, M sub 1, M sub 2, capital M. The worst case is it's also little m. Okay, that's the worst case, because then when you go to something else that's not little m, you're used to writing little m again, when it's not supposed to. Okay, Newton's third second law. And then the other one is sometimes you might have the free body diagram if you don't include it, because you have to know that it always works as well. It's always there, and that's Newton's third law. Right? Newton's third law always works. And this, the place where you can make a mistake is not seeing it in the, when you draw the free body diagram. So the force, say you have two objects. A, this is, and B, this is a homework problem of last week. So two forces,
I remember this one.
right? And
This one.
this is force. You have to really assume that you are A, and what's touching A, okay? Weight, gravity doesn't have to touch you, so that aside, you consider all the things that touch you, and if you're A, is the table touching?
Nope.
No. The only thing that's touching is B, right? So there's gonna be a force. Force on A due to B. Force on A due to B. And so, and then the other way, this force on the B, if you're so if you're A, you're gonna feel you're touching B, and B is to the right. It's always gonna be pushing the other way. There's no way it can push that way unless it's pulling with the rope or something. Okay, but this, if B is on the right, then it's the force is gonna be pushing the other way. So this one will be F on A due to B. And this will be the force. This is B, and you're gonna feel something from the left, so that must be force on B due to A. That's B due to A, and they're gonna be equal but opposite. So same magnitude but opposite direction. Force on B due to A. Now, that's not all. That's touching, but you can be touching and also have, this is a perpendicular force, right? This would be something like a normal force.
Yep.
But there's also be friction, which is something that's parallel to these surfaces. So if I do a free body diagram for A, and this is mass of A, we have the force on A, U to B, going to the left. We have the mass of A times G, the weight going down. We also have the friction touching, right? Because these two surfaces are touching, and it's going like that.
Plus F1.
Yeah, and if there's an external force, and it's actually touching A, so then there'll be F1. For B, F1 is not touching it, B directly, so you can't put it in there. It does have its weight. It does have a normal force from the flow. Then it has these two contact forces as well. This one and this one. So FAB is going to the left, and you'll have an FBA going to the right. And then you'll have friction, which is up, and B will feel the friction that's down. Okay. So this is how the third law comes into play. It gives you more forces than you might have missed. Right?
Wait, so there's no normal force on A?
Technically, that's FAB.
Yeah, there's not from the table, but there's a normal force from this, which we call FAB.
Okay.
Okay, so only a couple more things. So everybody knows weight is W plus mg. Everybody knows that normal force is perpendicular to the surface. And then the only thing I should really stress is about friction. Okay. So let's say, I'm sorry, let me, you have the weight. W equals mg, that's easy. You have 4, which is a normal force. And common, I've seen in the homework, the common thing was to put n's, just n. Again, you have to have, n or n1 or n2, but it's perpendicular to the surface. If your surface is at a ramp that's inclined, it's still perpendicular. In that case, you use tilted axes. And then the last is the friction. Okay. Friction, there's two kinds. There's kinetic friction. F sub k equals mu sub k times the normal force. The appropriate normal force, right? So here, this friction here, this friction between these two blocks A and B, what's the normal force that applies to that static friction?
FAB.
Yeah, FAB. Okay, definitely not this one, because that's over here. So it's the force that's making these two surfaces stick to each other. Okay. Very common mistake is students just leave that out. It's just mu k. For some reason, you call FK mu k, and then that's it. So you have to see that mu k is just from 0 to 1. If you just put the 0.5, obviously there's something wrong, right? It can't be just so small. You have to include this n. That's kinetic friction only when it's moving. It has only one value, only when moving, and always opposite the motion. The static friction is the one that's a little tough to figure out, because sometimes it can be pointing one way, and sometimes it can be pointing another way. Right? So if I'm trying to push this to the right, then static friction is opposing. But if I'm pushing it to the left, then static friction changes sign and goes the other way. So it can be either way. And then it can be anywhere from 0 to the maximum. Okay, so another common mistake is to immediately jump to calling it the maximum. It can be anything up until the maximum. After that, it turns into kinetic friction. And Fs max is equal to mu s times n, right? And how do you know which way to draw it?
Whatever opposite's pushing it.
So it's it's not 100% clear. Because if you have, say you have a bunch of forces, it all depends on, in the end, their values, right? So just draw it. Just draw it in. Say, I'm just gonna go that way, okay? And then in the end, if you get a negative number, that means it's actually the opposite of what you chose. Okay. And then when do you know to use max? You use go opposite the potential motion. Now, another way to figure out if it's not too complicated is to say, if it's not there, which way would I be going? So that's it's pointing the opposite of potential motion. And then use Fs max when something's about to move. When you see words like our min and max, use Fs max when words like max or min appear in the problem. And if those words don't appear in the problem, then don't assume that it's Fs max. Okay? And then the very last thing is centripetal force. And I've been telling you that your books like try to write it like this. Okay, it's not that one. Okay, that does not appear in a free body diagram. So you shouldn't even put this centripetal force in a free body diagram. Okay, so that's all I have